A DNA profile from a crime scene matches a suspect. The lab says an unrelated innocent person would match just once in a million. So, is the suspect virtually certain to be guilty? No. That number answers one question. If a person were innocent, how often would their DNA still match? But guilt requires the reverse question. Given this match, how likely is innocence? Imagine DNA is the only evidence, and police searched a database of 10 million people. Chance alone could produce about 10 innocent matches. Which one is the criminal? The DNA statistic cannot tell you. Other evidence, and how the suspect was found, must change the odds. Swapping those two probabilities is the prosecutor's fallacy. Rare evidence can be powerful, but evidence is not a verdict. To see the trap, separate two arrows that sound almost identical. Arrow 1 asks, if an unrelated person supplied the DNA, how surprising is this match? That is what a random match probability describes. Arrow 2 asks, now that we observed a match, how likely is this person to be the source? That is a different calculation. The first arrow begins with an assumption about the source and predicts evidence. The second begins with evidence and tries to reason back to a source. Reverse the arrow, and a tiny probability can suddenly masquerade as near certain guilt. But the reverse calculation is missing something. Where did this person come from? Consider two investigations with the same 1 in a million match. In the first, a camera shows one person entering a locked room. A witness identifies the same person, and only then does the lab compare the DNA. In the second, police have no suspect. A computer searches millions of stored profiles and returns one of the matches it was designed to find. The laboratory result may be identical, but the starting odds are not. The first suspect was already singled out by independent evidence. The second was selected by the DNA search itself. Evidence cannot update odds until some odds exist. That starting point is called the prior. It is not a guess pulled from the air. It represents what the rest of the case says before this particular result is added. This rule is often presented like a sacred equation. The useful idea is simpler. Start with odds, multiply by the strength of the new evidence, and get updated odds. For a clean single-source profile, the match can act like an evidence multiplier. With a 1 in a million random match probability, that multiplier is roughly 1 million against an unrelated alternative. If independent evidence made the source odds 1 to 100, the starting point already favors this person. The DNA multiplier then creates a very large advantage for the source, but begin at 1 to 10 million, as in our simplified database search, and the same multiplier produces odds near 1 to 10. That is roughly 1 chance in 11, not certainty. These are toy numbers, not a verdict formula. Their purpose is to expose the missing input. A giant multiplier can be powerful, but it cannot choose its own starting line. Now return to the database. A probability that looks microscopic for one comparison can behave very differently across millions of comparisons. At 1 chance match per million comparisons, 10 million unrelated comparisons produce an expected count of about 10 chance matches. Sometimes fewer appear, sometimes more. If the true source is also in the database, that person may be standing inside a group of matches created by the search. If the true source is absent, every returned match may be innocent. This does not make database searching bad. It makes a database hit an investigative lead, whose selection process must be remembered. The question is not merely, how rare was a match before we searched? It is also, how many opportunities did we give chance to manufacture one? Even the phrase 1 in a million is not a free-floating property of DNA. It depends on which genetic markers were measured, whether the profile is complete or partial, whether it contains DNA from several people, and which population data and statistical corrections were used. It usually refers to an unrelated alternative, a close relative, and especially an identical twin, changes the comparison, and it is not a universal error rate. 1 in a million does not mean one laboratory mistake per million tests. It does not measure contamination, sample switching, software assumptions, or whether the wrong object was collected. The statistic answers the question it was built to answer. Every word in that question matters. Now suppose the profile really did come from the suspect. Even then, the reasoning is not finished. Forensic scientists often have to separate 3 levels. The source level asks whose biological material it is. The activity level asks how and when that material reached the object. The offense level asks what the person actually did. A DNA match may strongly support a source proposition while saying much less about the activity. DNA on a steering wheel could come from driving the car during a crime. It could also come from using the car yesterday, repairing it last week, or touching someone who later touched it. whose DNA, and who committed the crime are connected questions. They are not identical questions. Modern DNA profiling is extraordinarily sensitive. That strength creates another trap. It can detect biological material without explaining its journey. In primary transfer, a person touches an object directly. In secondary transfer, one person passes DNA to another person, who then touches the object. More complicated chains are also possible. Contamination is different again. Extraneous DNA can enter during collection, transport, storage, or analysis. Laboratories use controls and strict procedures to reduce and detect these risks, but the random match probability is not the probability of contamination. An official court primer groups a perfect-looking match under three broad explanations. The suspect supplied the material. Another person shares the profile, or the result is a false positive caused by switching, contamination, or another error. One dramatic number cannot compare all three unless the model explicitly includes them. The danger is older than forensic DNA. In a 1968 California robbery case called People v. Collins, the prosecution described a couple using several visual traits and a partly yellow car. Then it assigned numerical probabilities to those traits, multiplied them, and arrived at odds of 1 in 12 million. The numbers looked scientific. The foundation was not. The individual probabilities had not been supported by evidence, and the prosecution had not shown that the traits were statistically independent. The California Supreme Court reversed the judgment. It warned that the calculation could not answer the crucial question of the couples who fit the description. Which one committed the robbery? The problem was not mathematics. It was mathematics asked to perform a task its inputs could not support, a probabilistic verdict dressed as proof. There is a mirror image mistake called the defense lawyer's fallacy. Suppose a profile might be shared by 20 people in a country. It is tempting to say the suspect therefore has only a 1 in 20 chance of being the source. That is also wrong when the suspect was identified by strong independent evidence. The other 19 hypothetical people may have no connection to the place, the object, or the event. The prosecutor's fallacy ignores the alternative candidates and the starting odds. The defense fallacy ignores the evidence that selected this candidate from the group. One mistake turns rare evidence into automatic guilt. The other treats rare evidence as nearly useless. Good reasoning does neither. A better forensic statement uses a likelihood ratio and two explicit propositions. For example, these DNA observations are far more probable if the suspect contributed the sample, compared with an unrelated person contributing it. Notice what that sentence does not say. It does not say the suspect committed the offense. It does not state the probability of innocence. It describes how strongly the observations favor one source proposition over a stated alternative. Then the fact finder combines that weight with everything else. How the suspect was identified, whether the object was connected to the offense, possible transfer, possible error, alibis, witnesses, and competing explanations. Whenever a rare statistic appears, ask 5 questions. Probability of what? Assuming what? Compared with what? Selected from how many? And what evidence is still outside the number? Return to the evidence table. The DNA match has not become weak. It has become correctly shaped. It can slash the plausibility of one alternative. It can connect crimes, exclude suspects, and transform a case when independent evidence points in the same direction. But it cannot choose the prior odds, explain how biological material arrived, absorb every error mechanism, or decide what happened. The deepest version of the prosecutor's fallacy is not simply reversing 2 symbols. It is confusing the strength of one observation with the truth of an entire story. So when a number sounds like a verdict, turn the arrow around and read the assumptions underneath it. A probability can measure the weight of evidence. It cannot carry the verdict by itself.